Welcome to our channel. Watch the video until the end. Leave a like, and subscribe to the channel to support us. The Voyager probes, launched in 1977, are still functioning today, 47 years later, thanks to the radioisotope thermoelectric generators RTGs. Each Voyager is equipped with 3 RTGs that generate power directly on board. Let's see how they work. Each RTG contains 24 spheres of plutonium-238 oxide, which is a radioactive isotope. During its decay process, plutonium atoms lose an alpha particle, consisting of 2 protons and 2 neutrons. These particles, colliding with the walls of the RTG, heat it up. The heat is then converted into electrical energy through silicon and germanium thermocouples. The decay process is unstoppable, so heat is continuously produced, regardless of its use, and this is why there are also heat sinks on board to eliminate excess heat. The Voyagers are the farthest probes from Earth and the only ones to have reached interstellar space. We still maintain contact with these probes thanks to the RTGs that produce energy. However, the plutonium slowly depletes due to its decay, so the Voyagers will progressively have less energy available. It is expected that we will completely lose contact with the probes in the coming decades, as the estimated lifespan of the RTGs is about 60 years. Already we have had to turn off most of the instruments on board the Voyagers to save energy. Many space probes use solar panels, but these become ineffective when the probe moves too far from the Sun. The farthest probe using solar panels is Juno, in orbit around Jupiter. RTGs were first used in 1961 aboard an Earth satellite. Subsequently, they have been employed in many space missions, including the Pioneer 10 and 11 probes headed towards Jupiter and Saturn in the early 1970s, the Mars rovers Curiosity and Perseverance, the Cassini probe that explored the Saturn system, and the New Horizons that visited Pluto and the Kuiper Belt object Arrokoth. Plutonium-238 is a limited resource and its management involves risks, given its radioactive nature. The RTGs of the Voyagers were installed just before launch. The European Space Agency (ESA) is collaborating with the British National Nuclear Laboratory to develop a new type of RTG that uses americium-241, an isotope that produces less energy compared to plutonium but for a longer period, up to 5 times longer. Americium is also less expensive and easier to handle, and for these reasons, the ESA is focusing on this isotope. In the United States, which still has stocks of plutonium-238, the adoption of alternative technologies such as advanced Stirling radioisotope generators ASRGs, which use about a quarter of the plutonium to produce the same amount of energy, is being evaluated. These radioisotope generators are currently the only tools that allow us to produce energy in deep space. On the other hand, it is interesting to note that, despite the technical and logistical challenges, RTGs have made possible not only the Voyager missions but have also paved the way for an era of deep space exploration that previously seemed unreachable. Their ability to provide constant and reliable energy without depending on sunlight makes them ideal for exploring regions of space where solar panels would be practically useless. These generators have been a true revolution in space technology, allowing probes to operate in extreme conditions for decades. This has allowed us to collect valuable data and send back images to Earth that have captured the imagination of millions of people and have helped to form the basis of what we know today about the outer boundaries of our solar system. Looking to the future, the search for alternative energy technologies for space exploration continues. The interest in americium-241 and ASRGs demonstrates a constant commitment to technological innovation, essential for future missions, including the potential sending of probes to the icy moons of Jupiter and Saturn, such as Europa and Enceladus, which might harbor life forms. Moreover, these developments represent not only a step forward in space technology but also in how we manage radioactive resources and our approach to sustainability in space missions. The ability to utilize less expensive and more abundant materials like americium could significantly reduce the costs and logistical complexities of future space explorations. As we continue the journey of human exploration of deep space, emerging technologies like RTGs based on americium-241 and advanced Stirling radioisotope generators promise to further expand our horizons. With these innovations, we will be able to probe even more remote and hostile environments, opening the door to missions that were once considered too bold or technically prohibitive. For example, future missions to the moons of Jupiter and Saturn, such as Europa, Ganymede, and Titan, could greatly benefit from these technologies. Europa and Enceladus, in particular, are primary targets in the search for extraterrestrial life, thanks to the suspected presence of vast liquid oceans beneath their icy surfaces. Advanced RTGs could provide the energy necessary to power probes capable of drilling through the ice and exploring these subterranean oceans, searching for signs of biological life. Similarly, our ability to remain operational in environments far from the Sun and in extreme conditions will translate into better opportunities to study the most distant and dimly lit celestial bodies in our solar system, such as the members of the Kuiper Belt and beyond. These mysterious places, which were once only a bright spot through telescopes, could be examined up close, providing invaluable data on the formation and evolution of our solar system and other planetary systems. At the same time, the growing focus on the sustainability of space technologies highlights a maturation in space thinking. As we continue to explore, it becomes imperative to do so responsibly, minimizing environmental impact and ensuring that resources, such as plutonium, are used effectively and safely. This effort also includes the search for safer and more abundant alternatives, like americium-241, which can reduce the risks associated with transporting and handling radioactive materials in space. Finally, the ongoing innovation in radioisotope thermoelectric generators and other energy technologies not only expands the possibilities for space exploration but also strengthens international collaboration. Projects like ESA working with the British National Nuclear Laboratory to develop new RTGs are examples of how global cooperation can overcome technical and logistical challenges, leading to discoveries that no single country or agency could achieve alone. In conclusion, as we bid farewell to the legendary service of the Voyager probes, we cannot help but look forward with excitement to future possibilities. The lessons learned from these pioneering missions will guide humanity as it continues to explore the most remote and uncharted corners of space.